All right, so we're here today introducing velocities and forces in two dimensions. I do apologize for the helter-skelter manner in which I'm showing this, but I've spent a lot of time trying to figure out how to summarize this. Please note that this is considered an introduction, and while physics certainly does have a lot more things that you can do with velocities and forces and vectors in two dimensions in general, obviously there's more measurements we can look at even other than forces and velocities in two dimension, but we're just starting here. And so this is just a good place that we're going to look at and do the best we can. To start with, we typically use vectors to show velocities and forces in two dimensions. And a vector is a measurement that includes size and direction. It's typically shown with arrows. By the way, when I do these, I'll expect you to pause or fast forward or whatever works best for you on these style notes, but I'll be scrolling through this document and doing some examples also via a couple other places. So oftentimes there's multiple forces or velocities happening at one time, often in different directions. We can combine them using vector addition. This is the process of finding the resultant vectors from two or more vectors. Now, there's two methods I'm going to show you. The first one is tip to tail. I think it's a little better conceptually. It's a good place to start. And then the second method I'll show you is X and Y components, and that's better, I think, mathematically. The tip to tail method, as it's stated there, you can read that and write it down. I'll show you what I mean in a second. We can think about an example might be a river crossing. So if we go over here to our simulation, this helps us think about velocities. Let's pretend there was a river, and let's pretend that it was flowing this way at the speed of 8. And this is kind of the river. And let's pretend the swimmer wants to cross the river. Let's pretend the swimmer's swim speed is also 8. Now if the swimmer jumps in here at point 20, move this out of the way, and starts swimming this direction, what's going to happen? Well, what's going on with the water moving this way? And before we think too much about that, it might be worth jumping back and thinking, well, what would happen if we had something like this? What if the swimmer was swimming with the river? How fast would they be going? Well, I think most of us would have a pretty good idea that the swimmer would be like a person on a treadmill, walking with the treadmill. I actually have an example of that right here. I don't know if it'll work. We'll see. Here you have a couple of kids. One's walking on a people mover. They're walking the same speed, but in that case, their speeds were getting added together, the velocities were getting added together. We can actually see that by showing this as a resultant vector. Now, and again, this would be if they're walking the same way. If we flip it around, let's turn that off. If we flip this around so that, let's say you happen to jump in that river and start swimming upstream, and you're swimming the opposite direction, these vectors might look something like this. As an example, here's these same two kids. They were at the airport. This is what you might get an example of something like that. And in fact, your resultant vector, would be 0. You can see that it's there, but it shows 0 when they're the same size. And the tip to tail method would be if you take the tip of that to the tail of that and you move it around, you'll see that, well, the resultant is actually 0. It'll make more sense in a second when I show you the way we can think about it in terms of a river. If we go back to our river example, this is the river flowing at 8. This is this guy that jumped in is trying to swim. And what we would find is when he's trying to cross the river, we can use the tip to tail method, and his velocity would actually be a result from the tail here to the tip here. This would be the resultant velocity of these two velocities that are being added together. In fact, we can see that, and I can move it over here to show you. Now, if this guy was trying to swim across the river, straight across, and not get swept downstream, what we would have to do is he would actually have to change his plan. He would have to swim. Let's move this down here. He would have to swim upstream at a pretty sharp angle. We can see there. He would have to angle into the current to barely move across horizontal. So you can see the value of this tip to tail method as far as seeing the results. I don't believe it works too well when we're dealing with too many things going on, and the method that I prefer, I'll show you one more quick thing here. This would be another example of tip to tail. Say you have three vectors. This could be forces or velocities or any other vector quantity, really. What would the resultant of these three be? Well, since we've connected them tip to tail, the resultant would be from the tail to the tip. And I do that in this next slide. I'll show you what I mean. So this would be the resultant vector if you added these three vectors together. This is great graphically and nice if you have some kind of simulation like this. But when you're trying to do it in actual, on pencil and paper or figure problems out, I find the x and y component, which is the second method, x and y component, to be an easier way. It's a little bit more math, but it's more commonly used in physics as I've seen and experienced it. You can write down this. I wouldn't freak out too much about these equations. I've got them listed below in a better format. But the x and y component, I'll show you the examples in a second, but you're basically using the sum of the x and sum of the y and then essentially solving for the resultant. So here are these equations that you had there. Now, please notice that this equation for force is identical to the equation for velocity. The only thing you're changing is if you have a force or a velocity. I can try to give you an example of that. We've seen velocities already. Let's look at a force. So let's say you happen to have a lovable physics teacher here who has tried to outsmart the system and is needing to drag a table across the room. It's worth noting that this rope right here is putting a force on this table leg. And if we think about what's going on here, we'll label an x-axis here. We always want to call x-axis 0 degrees. We'll label a y-axis here. And we can see that there's a force being applied through this rope on this table right here. Now, if we go back to thinking about x and y components, we can actually find the x and the y component of this. So if we go down here, there's an x component of this force, and there's a y component of this force. And we can find the values of those as long as we have the angles. And I'll show you that in a second. So this is a replication of what I just showed you in that picture. You have this upward force, and we have an angle. Remember, we're calling the angle from the horizon. So we can get this x and y value. So if we go back here, negative 12 and then 11. So this value here would be 12. It's to the left, so we'll call it negative 12. And this value here would be 11. Interestingly enough, this is very close to exactly the same x and y components. I didn't do this on purpose, but I just naturally grabbed a hold and as if I was going to drag the table. And you can see that probably just through time and experience, I've learned that if you have around a 45-degree angle here, your x and y components are about the same, and you can actually maximize your dragging power if you're pulling upward at about a 45-degree angle. That's just a little side note. Moving along here, we are familiar with seeing force tables like this, force diagrams. What we just saw was something like this, where we have this weird upward angle. What's going on? The power of x and y components is we can get rid of this weird thing here where we're not sure what would happen, and we can reduce it to its x and y components. So there's a x component. I guess I skipped that. There would be an x component here, a y component here of this force, and we can put those over here on that, and then this looks a lot more simple. So this is trying to show you the value of those x and y components. If we go back to the addition of that, remember we said we could add using x and y components. I have this set up here. This is exactly the same scenario that we showed before with the tip to tail method. And I know that when you look at this, it looks like a mess. And that's just the way this simulation shows it. But if we move down here, I want to try to show you the value of this. I just moved these vectors out so we would have space to look at them. And we found the x and y components of all of them. You have the y component, y component, y component, x component, x component, x component. And we can just add up those y components. You would have 7 plus 8 plus 1. That's going to be 16. That's going to tell you the value of the resultant vector's y component. Then we can add up the x components. 6 plus 9 plus negative 11. The x component would be 4, and so that would be 4 here. And so if we start here, we could quickly see our resultant vector is positive 16, y, positive 4x, and so then we could find the direction of this graphically. Now, of course, if we were using Pythagorean to solve this, this is actually a right triangle because x and y, the x and y axis intersect at a 90-degree angle, and so we could find that, in fact, I can just show you right here. These intersect at a 90-degree angle. And so this would be two sides of a right triangle. So this would be the C side. So you could use Pythagorean and you could say 4 squared plus 16 squared equals C squared. That's how you could find the magnitude. And as mentioned before, if you wanted to find that value of it, we scroll back up here. Sorry for all the scrolling. You wanted to find the value, you could use any of these equations and just solve for theta once you have that magnitude, which is, if it's a force, you of course could use this one. Force and velocities the equations are identical, but, so here's what I'm saying here. Direction can be found using the equations and solving for theta. All right, I do believe that's it. Thank you, and I hope you have a great day.